Now we have learned a lot of new functionalities in OpenCV. And in this video, we are going to put everything together in order to develop a colored ball tracking application. So in this video, we're going to take as an input an image of a ball, and then we will identify the ball inside the image using color filtering, and then we will detect the contour of the ball, draw its center location, and surrounding it with an enclosing circle. We're going to apply all the knowledge that we have learned in the 3 previous lectures in order to develop this application. So the algorithm will be as follows. Now I think you understand the steps. We're going to read an image as an RGB image, and then we will use color filtering techniques in order to identify the ball by its color in the image. So we're going to have kind of a mask where the ball will be colored in white and everything else will be colored in black. And then we will have a binary image that will represent the mask. We will use it as an input to contour detection. So we will find the contour for the ball, and finally we will identify the center weight of the ball and draw the surrounding circle around the ball. Let's see how we can implement this in practice. Let us now consider the code ball detection.py. So basically, we're going to use some of the functions that we have defined in the previous videos. Of course, first of all, we need to read the RGB image. Okay, so I'm going to use the same function used in the previous videos. And also, the second step is to use this RGB image and filter the color using the lower bound color and the upper bound color. We're going to use the same lower bound and upper bound that we defined for the yellow color in the color filtering lecture. Okay, so filter color is going to return the mask, which is a binary image. So in this particular case, we don't need to use any kind of thresholding techniques because the in-range method that we will use here is going to return a binary image, which we call here the mask. Then the mask will be used as a binary image input for the get contour method, which will be using the 5 contours method of OpenCV, and then generate all the contours. So after that, we will draw the ball contour. We will use the RGB image, the binary image, and the contours. So basically, it's the same process that we did before. The only difference here is that we are going to choose a certain area threshold for which we're going to draw the contour of the detected object. So we will see that this condition is very important to eliminate some of the small contours that does not represent a yellow tennis ball. So this is the algorithm that we are going to follow. First of all, we take the name of the image. We define the yellow lower bound and the yellow upper bound for the color. So these are basically the same bound that I have explained in the color filtering lecture. Then read the image. Okay, so we're going to read the image and generate an RGB image. Then we will generate the binary image mask by applying the filter coloring technique. The filter coloring technique is going to take the RGB image and the upper and lower bounds, and then we will generate the binary image mask. Then we will use this binary image to generate all the contours, and then we will process the contours to draw only the contour of the ball. So basically, we have used most of the functions. The only difference, as I already mentioned, is just we have made here the area of the contour. So let us now execute the ball detection. Okay, so the ball detection here is going to be applied to tennis ball 1 image. So let's see what happens. Now this is the tennis ball, and now this is the contour of the tennis ball, the surrounding circle in red, and also in the center here we can observe a center point which we have calculated here. I added cv2.circle in the black image. Okay, I just create a small circle of radius 5, which is fill. So I use -1 to make it fill. Add the center point cx, cy. And the outer circle here, this is actually the surrounding circle or the enclosing circle that we have calculated its radius here. So now let's apply the same code. So if we use here very small value of the radius. Okay, let's try what happens. So in this particular image, we don't have any problem because it's clear that we have only one yellow object that is the ball. So let's try other images. So I'm going now to run the algorithm for the second ball, tennis ball 2, and here it matters a lot. So you can see we have very, very small things because we have a lot of yellow to green colors which are like filtered by the filter. So they are kind of considered as detected objects, and they are not. So one of the things we can do here to improve, okay, is to change the area. Okay, we want to print very large area. For example, here I'm going to use 2000. And you will see now we're going to have much better. Look, we have eliminated most of the very small detected objects. And here, of course, you can see that we have two circles for the same ball because basically this line that comes in the middle, it makes it like they are two separate objects. Okay? So this is one of the problems of color detection. It's very sensitive to other colors. Okay? Although for us, we look as this is only one object, but for color detection techniques, it is identified as there is an object here in the left and another object in the right. And look here, some kind of edge is detected because maybe it matches the criteria of the filtered color. But of course, maybe what we can do, so you can see these are the different areas that we have here. So maybe we can select an area greater than 3,500, or this one is 35,000. So let's make it greater than 10,000. So in this case, we're going to have only the ball itself, which is not bad. So you can see now the criteria of the area is actually important, and it will differ from an image to another. So if I select the image number 3, image wall number 3 here, of course nothing here is detected because we don't have any contour that has an area greater than 10,000. So maybe because the image is small here, we can start by 100 just to check. Okay, and it's detected. It's pretty much fine. But of course here, due to the shade, the color filtering did not work pretty much fine. Maybe we need to tune a little bit the saturation and the brightness in order to have a more accurate detection of this object because of the lighting effect. We can try another image, number 4. We have 5 images of tennis ball. So same thing here. You can see when we have a big tennis ball and this separation here matters a lot. So we can actually increase the area again to avoid having two duplicated contours or edges. So we can see we have two areas, 12,000 and 46,000. Maybe you can choose this one, the biggest, 30,000. Okay, and again we have only one contour detected. Okay, so let's apply on the last image number 5. Of course, here we have very small wall, so we need to change the area again. And it is correctly detected, as you can see. So you can see it's possible to use color filtering together with contour detection in order to detect objects based on their colors. But you can see also that this technique is not very robust, but it can do the job in very specific contexts and use cases. Of course, nowadays, there are much more sophisticated techniques in computer vision and image processing, and basically they rely on the technique of deep learning and neural networks, which is able to classify and detect and recognize different type of images with high accuracy. Now, having completed with ball detection applied on an image, you're going to extend this program to develop tennis ball tracking application. So a tracking, it means we're going to apply it on a video. In this case, the ball is going to move. So let me show you the final expected output that you need to do. Okay. So you need to extend the current code in order to develop a ball tracking application. Okay, so you can see this is the real image and this is the contour image. So you can see here we have ball tracking, and basically we use the same code. So all you need to do is to read the video stream and then process the frames one by one. And in every frame, you need to apply the ball detection algorithm. So in the assignment, you will do it in two different ways. The first way, you're going just to read a file using OpenCV. You will read a video file using OpenCV and process it frame by frame. The second part of the assignment, you need to read from the file and publish the frames using an image ROS topic, and then you subscribe to the topic and process the frames in the same way. So in the second part of the assignment, you will need to use ROS bridge in order to make the appropriate conversion of the image format from OpenCV to ROS and vice versa. So you will have more details about the assignments in the assignment page following this video. بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. In the next few videos, I'm going to talk about how to work with OpenCV in C++. The principle is almost the same as in Python, however, there is a little bit of differences on how to execute the programs and also in the syntax. So I'm going to cover a few of the topics I have covered in Python. Like in this example, I'm going to show how to open and save images, and then I will show how to read the video stream and also how to work with CV Bridge in C++. Let us consider the code readvideo.cpp, which is in the folder topic 03 perception. In the folder CPP, we have the file readvideo.cpp. So first of all, we need to include OpenCV2 library, and here the syntax is include opencv2/opencv.hpp. So this is the header file, and then we create a main function and we define an object called video capture. So video capture is going to open the default camera with index 0, and then if the video capture is not opened, we're going to exit the program and return -1 as an error code. And in case of success, we're going to start an endless loop and we create a frame. So Matt defined the structure for an image or for a frame. In the while loop, we're going to use video capture object in order to collect every frame. This symbol is going to get a new frame from the camera. Okay, it's going to return a new frame from the camera and assign it to the frame object. And then you can do the classical OpenCV operations. Like for example, we can convert the frame into a grayscale image. So we take the frame as input and the edge as output, or maybe I'm going to call this as gray image. I'm not going to consider edges here, but just a gray image. And finally, we will use IMShow like in Python in order to print the gray image. Of course, we can do even more processing like Gaussian blur or also extract canny edges. I have just disabled these two operations. I'm going just to show the gray image as it comes. And finally, we wait for 30 milliseconds. If a key is pressed, then we're going to exit the while loop and we return 0 to exit the program. So this is our code. And now if we want to execute it, it's not like Python. We have to create a new executable into the CMake list. So how can we do that? Let's go to cmakelist.txt and going to the bottom. So first of all, we need to add the package OpenCV, find package. We can also add it here in the top, in the find package section, okay? Like we added ROSCPP, ROSPy. We can also add here OpenCV, okay? In this case, it's just added here in the bottom just before declaring the executable. So this is a required instruction, find package OpenCV. It's going to include the package for in the compilation and also include the directories for OpenCV. We include directories, OpenCV, include gears. And then this instruction is going to add a new executable. So this is the name of the executable we will create, read video CPP. And this is the source file that we have just presented and edited here, this one. Okay, and after creating the executable, we need to link the libraries. First of all, we link the Catkin libraries to the executable. And also here, and this is something new, we need to also link the OpenCV libraries. So look, for example, in the simple programs that we did before, we just needed, for example, for the listener node, we just linked it to Catkin libraries because here listener node did not use OpenCV. However, if you use OpenCV, you need also to make sure to add target link libraries to the executable, and here you will add the OpenCV libraries as well in the same way you did it for the Catkin libraries. Now we have everything in place. After doing that, we can go to the Catkin workspace and then compile using Catkin make. You can see now read video CPP is now executed, and now I can run the code. First of all, I'm going to run roscore. And then on a new terminal, you will use rosrun, ros essentials CPP, read video underscore CPP, and then we execute. So you can see now we have the gray colored image. So we capture the frame from the USB camera, and then we convert it to a gray image, and then we display it using IMShow. So this is an example on a C++ program with OpenCV. In the next video, we are going to see how we can read images and save them to a In this video, I'm going to present how to open and save images with OpenCV in C++. So let's see how it works. Let us consider the file open_copy.cpp, which is located in topic 03 perception in the folder CPP. So first of all, we need to import the different libraries related to OpenCV, and then we define the main function, and we define an image structure using the class math, which is a class defined in OpenCV that defines the structure of an image in C++, and then we will read the image from a file, okay, which is located in a specific path. So basically we're going to read this image that is called chess.jpg, okay, and here I specify the absolute path of the image, okay, /home and then the name of the image.jpg. So I specify the absolute path because later on when you execute the C++ program, if you just specify a relative path here, for example, if you just mention chess.jpg, in this case you have to execute the node from the same folder where this file is located. If you specify only the file name, you have to execute the node from the same location and the same folder of the file where it is located. However, if you use here the absolute path, in this case, independently from where you execute the code, okay, it will be able to find the correct file and then use it to open the image and then assign the image to the image object that is created here. And then the second parameter of the method is cvload_image_color, which means we would like to read the image as a colored image. And then we are going to make a validity check whether the image is correctly read or not. So if not image.data, and this means if there is no data found in the image, for example, the path was not correct or the image is not found, in this case, we're going to output an error message, could not open or find the image, and then return -1 to exit the main function. So the code will not continue the execution because the image was not found. And in case of the image is read correctly, we're going to create a named window, and then we will use the method imShow or image show to display the image. In addition, we can save a copy of the image into a file, okay, using the method imWrite. So here we specify the path. I'm going to save it into the home directory in temporary folder, and then I will call it image.jpg. Then the second parameter is the image object itself. And finally, it will wait a key. When I press a key, it's going to exit the program. So let's try to execute the code. In order to compile the file opencv.cpp, we need to add the executable into the cmakelist.txt. The process is similar to what we did in the previous video. Of course, we have to make sure that we use find package opencv and also include directories opencv include dir, and then we will add the instructions for adding the executable. And here we add executable opencopy_cpp, and then we specify the source file, which is this one, and then we will link the libraries to Catkin libraries, and also we will link the executable to the OpenCV libraries. Once this is done, we can go and compile our code using Catkin make. So now let's run the program. So first of all, we need to compile our code. Okay, now it generates the executable for OpenCV_cpp. Let's check first the TMP folder. This is the home temporary folder. There is nothing here inside. And then I'm going to run essential cpp opencopy_cpp. This is the name of the, and then we display first the original image that is read, and this is the chessboard. And then coming back to our temporary folder, we can find now the copy image. Okay, so using imWrite, okay, in the temporary folder, we can find now the copy image already created using this method. And imShow has just displayed the image that we have read from the file. And this is the original image that we have read. It is located. So in the next video, I'm going to show you how to work with ROS bridge in C++, and I will present how to convert an image from OpenCV format into ROS format and from ROS format into the OpenCV format. So let's see how it works. When you work with ROS, the image format in OpenCV and ROS are different. We already did a program in Python using CVBridge that converts between OpenCV format to ROS format and from ROS format to OpenCV format. In this video, we're going to do the same, but using the C++ language. I'm going to present how we can use CVBridge in C++ with ROS and OpenCV. The first thing you need to do is to make sure that you have the latest versions of OpenCV and also of CV Bridge. In some cases, if the CV Bridge version is outdated, you may find problems later on to compile your programs. So it will not hurt to use sudo apt-get update to update your system repositories. And then we use sudo apt-get install ROS Kinetic OpenCV. Okay, so now I am sure that I have the latest version, and also we do the same thing for CV Bridge. Okay, I have also the latest version. Then let us consider the code image pub sub.cpp that is located in topic03_perception in the CPP folder. So first of all, we need to include the required OpenCV libraries, and here we will include the image transport library, which is used to define the transport protocol for streaming images. We will also import the CV Bridge library and the other OpenCV libraries, ImageProc and HiGUI. So here we will follow an object-oriented programming version, although you can also do it without using classes. But we're going to define a class image converter, and then in the main function, we're going just to create a new object from image converter, and then all the work will be done in the constructor. So here we define some attributes for the class, including a node handle, the image transport called ID, the image subscriber, and the image publisher. So what is the objective of this program is to read a video stream from a USB camera, for example. It can be from any camera. So we're going to subscribe to a topic, okay, using image subscriber. And then we will do some modification for the image. We will do some processing, for example, printing something. And then we will publish again the image using a publisher on another topic. So this is the idea here of this program. That's why we will create a publisher and also a subscriber. So the difference here, the subscription is not going to be done using the node handle as we did in previous programs, and this is one of the differences between the subscription to a topic and to the subscription of an image in C++. So in Python we didn't notice that difference, but here in C++ we need to create an image transport object that we will use in order to create a subscriber for the image topic, and also to create a publisher. So we're going to advertise here the produced image, and we will publish it into another topic. So it's going to be called image_converter output video. So this will be done here into the image converter, and of course we need to initialize also the node handle, okay, by calling the constructor of the image transport. Okay, we can create also a destructor here whenever to destroy all the windows when the application will complete. And here in the subscriber, we will define the image callback, okay, associated to the class image converter that we define here. And the image callback is going to take a pointer to an image, which is defined here in MSG. And then we will create a new object, a new CV Bridge object as a pointer here, and then we will use the method CV Bridge to CV copy. It means it's going to make a conversion from ROS format to OpenCV format. It will take the message that we receive from the callback function, and then it's going to convert it to an OpenCV frame format, and this is the encoding of the image is going to be BGRA. Once the conversion is done, we can now look at the information of the image. We can use the CV Bridge pointer in order to check the number of rows of the image and the number of columns of the image. If it is greater than 50, okay, we're going to draw a point at this location, 50-50, with a radius 10. And then we will use IMShow in order to display the image that we have collected. So this is now the OpenCV image, which is collected using the CV pointer arrow image. Okay, so this is how we can collect the OpenCV image, and then you can access its different attributes, for example, number of rows, number of columns, or the image itself that we want to display using IMShow. Okay, so this is going to open a window, and then we'll display the image coming from the video stream. And what we can also do is to publish the new image. In addition to displaying the original image, we can create another topic to publish the image. So we will use the image publisher dot publish, and here we will use this method, CV pointer to image message. What does it do? It's going to convert the OpenCV image into the image format supported by ROS, and then it will publish this image into the ROS ecosystem. We can collect this image by just creating a subscriber to image converter output video. Of course, the subscriber that we will create, it will be of type image from the package sensor MSGS, and this method to image MSG is going to convert the message from OpenCV format to a ROS message of the type sensor MSGS image. Now we are ready to compile and execute this code, and of course, like any C++ program, we need to add this into CMakeList, and here there are a couple of things that we need to add. First of all, we need to add two packages, the CVBridge package and the image transport package into the dependencies needed by this project. Okay, so in the find package, we need to add CVBridge and also image transport, because these two libraries were included into our C++ code, CVBridge and also image transport. So we need to add these packages into the CMakeList. And then we need to create the executable. So we will add an executable, and this is the name of the executable, image pub/sub cpp. We specify the source file. This is the source file that we have just explained and presented here. And like we did with the previous codes, we need to add the target libraries, cat-kill libraries, and also we need to link the OpenCV libraries to the executable image pub/sub cpp. And of course, we should not forget to add the package OpenCV and also to include the directories. So this is already done for the previous code, and it's also valid for the new executable that we are adding now. So after doing these changes, we can compile our code. Okay, so you can see image pub/sub cpp is now created. Of course, now we need to run several programs. We need to run the driver for the USB cam, okay, which is ROS run USB cam node, and we need to run also an image. We need to run several nodes. Instead of running them one by one in a terminal, it is more effective to create a launch file for creating all these different nodes and starting them all together. So for this, you can go to the folder topic 3 perception cpp launch, and you can open this launch file. So remember that a launch file is a file that allows to start multiple nodes at the same time. In this case, we want to start 3 different nodes. The first node is the USB cam node, which belongs to the USB cam package, and this one is the driver of the USB cam. Is going to start the USB camera streaming, and here a certain number of parameters that we need to adjust. For example, we have to specify the video device being the first device at /dev/video 0. This refers to the first video device connected to the computer. The image width, the image height, these are optionals. We can put them. The pixel format, this is actually required. And also, we're going to remap the image topic to be camera/image raw. The second node will represent the image view node and is going to subscribe to the topic USB camera node image raw, okay, which is going to correspond to the topic of this image, of this node, because here we have the node name is USB camera node, so this is the node name, and this is the name of the topic that we are going to use here. And same thing, we're going to start the third node, that is our image pub/sub cpp, and here we're going to remap the topic name image. So we're going to remap the topic name image into the topic name that is going to be published by this node. Of course, we can add a fourth node that is going to subscribe to the following topic, image converter output video. And now we have a launch file that is going to start everything at once. So everything is ready now. Okay, our program is already compiled. Now we can use ROS launch, ROS essentials cpp, and then you have image pub/sub launch. So let me start this node. Okay, there is one small error that we can fix. There are multiple nodes that are named image view node. It's going to be easy to fix that because we have this node has the same name as this node. So let me call this one image view 2 node, and then we can start the program again. Okay, so you can see now we have three windows. This is the window that subscribes to the original image. Okay, this is the second window that we have opened in the launch file, okay, which subscribes to this video stream. Okay, because now we differentiated using the size that is bigger, 1280 and 720. And this one is the third window that subscribes to the image output video. This one that is published by the image pub subnode that we have created. So this is an example on how we can use CV Bridge in order to subscribe to an image, convert it to OpenCV format, and then publish again the OpenCV format into using a ROS publisher. So you can clearly observe that working with OpenCV in C++ and ROS is much more complicated than working in Python. This is why my recommendation is actually to do most of your programs in ROS with Python, because it's going to simplify more the development process. Unless you want to have real-time execution, in this case, it's going to be worth investing your time in developing with C++. Hi guys, and welcome back to a new tutorial in the course Robot Operating System Basics Motion and OpenCV. So far we have covered a lot of different concepts, including ROS basics like the ROS file system, ROS topics, ROS node, ROS messages, ROS services, and different things. And then we have talked about motion and how to make a robot move, what are the different topics that are responsible for making the robot move, and other topics that are responsible for finding the location of the robot. Of course, we have applied this on a turtle sim simulator, and in future lectures we are going to talk about more realistic robots. And then in the third part we have talked about OpenCV, which is about robotic perception. So today I'm going to talk about a new tutorial, how laser scanners or laser rangefinders work. And this is actually another way of robotic perception. So the robot can actually see the world using a camera, and for this we use tools like OpenCV in order to process the images and the video streams coming from the camera and extract useful information from them. But the problem, the camera only provides us two-dimensional information, only a picture. And a picture doesn't say anything about, for example, the distance of obstacles or the distance of objects from the robot. And for this we need a third dimension, which is actually obtained using a specific device like rangefinders, or we call them also laser scanners. And these devices are able to find the distance to objects. And they are pretty much useful in several types of applications. So let's see how these laser scanners work. So what is a laser scanner? Basically, it is a device that can measure the distance to obstacles. And there are several devices, not only based on laser, there are also ultrasonic sensors which are based on sound in order to determine the distance to obstacles. But laser scanners or laser rangefinders are based on a laser to detect the distance to obstacles. So how do they work actually? A device like the following is going to send a laser beam in different directions, and then these lasers are going to bounce back when they hit an obstacle, and then are going to be captured by a camera. So knowing the offset between the laser source and the camera, it is possible to estimate using the time of flight, because the laser travels at the speed of light. It's possible to estimate using time of flight the distance to the objects. And these devices are actually very useful in several robotics applications. For example, they are used in SLAM application for building a map, and SLAM, it means simultaneous localization and mapping. They are also used for obstacle avoidance. Without lasers, the robot cannot know the distance to obstacles, and in this case, it can easily hit any obstacle that comes in his path. So for example, when we worked with the turtle sim, we just used kind of blind navigation, okay? We didn't consider any obstacle, but this is not realistic. A robot, when it operates in an environment, it will have to manage how to avoid obstacles in his path. And for this, we need rangefinders like laser scanners or ultrasonic sensors. And for this reason, laser scanners are crucial and important and necessary for any navigation mission of the robot. So that's why the objective of this section is to understand how the laser scanner works, how we can connect a laser scanner to ROS, how we can read the information coming from the laser scanner, what are the meta information or the metadata of the laser scanner. All of these are going to be described in these coming lectures. So if you have a robot and you want to do navigation with the robot, the first thing you need to do is actually to get or to purchase a laser scanner. But here there are several available devices in the market, and there are a lot of characteristics that we need to understand, and there are a lot of features that will help us making the correct decision about which laser rangefinder is appropriate for our applications. So for any laser scanner, these are the main characteristics that you need to figure out before selecting it for your application. First of all, a laser scanner is characterized by a minimum angle and a maximum angle. So this is how a laser scanner would look like. It will send a beam of laser, over a certain angle, and here we have the minimum angle and the maximum angle. And the total field between the minimum angle and the maximum angle, it represents the field of view. And different lasers have different field of views, and of course this will impact their cost, their performance, and so on. As you can see in the picture, the laser is going to send several laser beams from the minimum angle to the maximum angle, and you can see here we have separate beams, and there is an angle difference between one beam to another, and this angle difference is called the angle increment, and this represents the angular resolution of the laser rangefinder. Also the laser scanner is characterized by the time increment, which is the time between the measurements. We're going to send one measurement and then another one, and the time between two measurements is called the time increment. And this time increment is different from another time that is called the scan time, which is the time between two scans. And one scan, it means sending all the different beams. So this is one scan, and then after getting all the measurements, we send another scan. So we have the time increment, and we have also the scan time, that is the time between two different scans. A very important characteristic of the laser scanner is the range. And for this, we have the minimum range and the maximum range. So the minimum range, it represents the minimum observable range. And for example, some sensors are not able to see objects that have a distance lower than, for example, a certain range. For example, some sensors cannot see objects that are in a distance lower than, for example, a meter or half a meter. Now, this is a characteristic that may differ from one laser scanner to another. And a more important characteristic is the maximum range. Some sensors are able to see, for example, only 4 meters away. Some other sensors, they can see 10 meters away, or 20 meters away, or 30 meters away. So the maximum range will depend from one laser scanner to another. For example, if you work in an indoor environment, in this case, maybe 4 meters will be sufficient. However, if you use a 4-meter scanner in outdoor environment, it will not make much sense, because in outdoor environments, spaces are larger and longer. So usually we use 20 meters or 30 meters. And of course, this will have major impact on the cost. The longer the range is, the higher the cost will be. And of course, the laser will return as the list of ranges. So you can see here, every laser that is going to propagate in the space is going to bounce back whenever it reaches an object. And then when it bounces back, the laser is able to estimate the distance to that object from this laser beam. So here, for every laser coming back, we're going to have an array that will contain the list of ranges, and then in ROS we can actually collect the list of ranges and then process them, for example, to build a map or to avoid obstacles or to perform navigations and so on. And finally, we have also the list of intensities coming back from the laser scanner. So this is an illustrative example, for example, of a laser scanner that will hit obstacles, and then we will see that every laser beam is going to represent one range. So at the end, in ROS, later on, you will see that we can have an array of ranges, and every range, for example, this is the minimum angle, will return 1.2, and then the angle just after that will return 1.3, and then 2.0, and so on, depending on the value that bounces back from the laser scanner after it hits an obstacle. So the distribution of ranges may look something like this. We can collect it using ROS, using software APIs, and then we can process this information in order, for example, to avoid obstacles or build the map. So something very important to notice is that the front direction is the angle 0, and then you can go to the right side, you have the minimum angle, and to the left side you will have the maximum angle. For example, here we have a field of view of 90 degrees between 0 and minus 45 and 0 and plus 45. In the next video, I'm going to present the most popular and common laser rangefinder available in the market. So let's look at some commercially available laser scanners. There are several devices available in the market, and I'm going to provide an overview of the most important ones that are used in ROS-enabled robots. For example, one popular and famous laser scanner is the Hokuyu URG4LX UG01. So this one is characterized by a maximum range between 0.1 and 5.6 meters. So this is the maximum distance it can observe is 5 meters or around 5 meters. And it has a nice field of view. It can look at opening of 240 degrees. So this means an angle between minus 20 degrees and 120 degrees. And basically this is useful in indoor applications because 5 meters or 4 meters is not sufficient to be operational in an outdoor environment. So you can see the scan frequency here is 10 Hertz. It means it's going to span 100 milliseconds per scan. So in 1 second, it's going to scan 10 times the ranges. So this is not very high frequency. For that reason, it operates on a low voltage and generates low current. It's only 5 volts because the interface is USB, so you can plug it on any USB 2 port, and 5 volts will be sufficient to power the laser scanner, and it's going to generate only 0.5 amperes. So the price is a little bit more than $1,000. On the right side, you can see another also popular laser scanner, which is currently used in Turtlebot 3 robots, which is the RP Leader A2, and there is also the new version A3. Okay, this one, it has a maximum range of 6 meters. It has a little bit longer range than Hokuyu RG04, and it has a maximum field of view of 360 degrees, so it can observe all around its environment. So it has an angle between minus 180 and 180. So you can see the field of view here is bigger because here this laser scanner is actually will keep rotating. This one doesn't rotate, it has just a static field of view, and this one is going to rotate, and for that reason it's able to view around of 360 degrees. It's used in indoor environment because of the short range. It can also at 10 Hertz, and it operates at the same nominal voltage, 5 volt and 0.45 ampere. It doesn't have a USB interface, but it has UART interface, which can be connected to a serial port on a computer, and the cost is much less expensive than the Hokuyu RG. It's only around $470. These are more sophisticated and advanced laser scanners, which are typically used in outdoor environments. So we can have the 6LMS 151, which has a maximum range of 20 meters and a maximum field of view of 270 degrees. And basically it is used in outdoor environments. So you can see here the scan frequency is even higher. It can sample scans at 25 Hertz up to 50 Hertz. And for this, it will require a higher voltage, so around 10.8 volt. It has different interfaces, not USB, but it has Ethernet interface, serial interface, and a CAN bus interface. And this price is, you can see, it's much more expensive. It's more than $5,200. So basically, laser scanners with good performance, they are very, very expensive. On the right side, we have the Hokuyu UTM30LX, and it has a maximum range of 30 meters, which is very long, and a maximum field of view of 270. It's used in outdoor environments, and it can sample at 40 Hertz, which means 25 milliseconds per scan. It operates on a voltage of 12 volt and generates 0.7 ampere. It has a USB 2 interface, and the price is more than $4,700. In addition to laser rangefinders, RGB cameras also are equipped with laser scanners. And RGB cameras are known to be depth camera. So why we call them depth camera? Because they have a stereo camera here, okay, which are going to provide a 2-dimensional image, and then the laser scanner is going to provide an information about the depth. So these cameras are able to generate depth images which are 3-dimensional. And what you can see here in the left side, even for Astra S or for Intel RealSense, this one is actually the laser scanner. So the characteristic of the laser scanner of this RGB camera, Astra S, can look up to 8 meters, and it has a maximum field of view of 60 degrees horizontal, 50 degrees vertical, and 70 degrees in diagonal. It is basically used in indoor applications, and the depth image size is 640 multiplied by 480 VGA 16-bit, 30 frames per second. It operates on 5 volt, and it has a USB 2.0 interface. The cost is around $170. On the right side, we have the Intel RealSense camera R200, which has a maximum range of 3.5 meters. It has almost the same maximum field of view, 60 degrees in horizontal, okay, 50 degrees in vertical, and 70 degrees in diagonal. It's used in indoor environments. It has a scan frequency of 40 Hertz, operate on 5 volt, and has an interface USB 3.0. The price is similar to the Astra S. Another type of laser scanners is the LiDAR Lead, and this one is the LiDAR Lead version 3. And basically this one is actually doesn't make several measurements. It makes only one measurement per scan, which is in the front direction. Okay, so it has only one laser beam, and it's a compact optical distance measurement sensor. This one is used in several applications, especially for example in drones. They are put on the bottom of the frame, so it can estimate the altitude of the drone or the distance to ground. It's going to look to the ground, and then it can be used to estimate the distance. So as I mentioned, it only returns one measurement value that is in the front direction, and you can see here it can reach a very high range, up to 40 meters. So it operates on 5 volt DC, and it can be used in both indoor and outdoor environments. The optical aperture is 12.5 millimeters, and it has two interfaces, either I2C or PWM. And it can generate at very high frequency, up to 500 readings per second. And the price is around $130. So this was an overview about the laser scanners and their main characteristics. And I have also presented an overview of the commercially available laser scanner devices. In the next videos, I'm going to show some concrete examples of laser scanners, how to connect them with ROS, and how to extract their information, like for example the list of ranges, the maximum angle, the minimum angle, the maximum distance, and all the information, and so on. And as I mentioned before, understanding how laser scanner works is really important and crucial to understand later on how the robot navigates and how to avoid the obstacle. Hello guys, and these are the two devices we are going to show how to connect them to ROS. So in the left side we have an ASUS Live Pro camera, which has a range of 4 meters. And as you can see here in the right side, it has a stereo camera, a pair of 2 cameras. And here in the left side, it has a laser scanner. So this RGB camera is able to generate depth images, and also it's possible using ROS to convert the depth image into a laser scanner. So we will see in a moment how to do that in ROS. In the left side, we have the Hokuyu URG device, which also has a range of 4 meters. And the difference between the two devices is that the RGB camera has a field of view of only 60 degrees, which is a little bit narrow as compared to the laser scanner, which has a field of view of 240 degrees. So of course the performance of the Hokuyu is better in terms of the field of view. It allows to detect obstacles at a wider range, but both of them operate at the same maximum distance, which is around 4 meters. Let's illustrate how to connect and to interact with these two devices and how we are able to observe the ranges collected by these two devices. In this video, I'm going to demonstrate how to start an RGBD camera and connect it with ROS, and how to convert the depth image into a laser scanner, and how to visualize it using ROS Topic Echo and also using RVs. In this demonstration, I'm going to consider the ASUS Live Pro RGB camera, and this is the description of the process. So first of all, we need to start the drivers of the RGB camera, and for this we can use the OpenNI 2 package that comes with ROS. So first of all, we need to make sure that it is installed. I'm going to show you how to do it, and then we need to start it using ROS launch OpenNI2_launch OpenNI2.launch. So this is going to start all the drivers that will be responsible for connecting with the RGBD cameras and extracting all the information and publishing them as ROS topics. It has to be noted that OpenNI2 is a generic driver. It works with many commercially available RGB cameras, and like for example Microsoft Kinect. So for Indigo and earlier versions, the default RGB camera that is used by the OpenNI2 driver was the Microsoft Kinect camera. Starting from ROS Kinetics, the default RGB camera is the ASUS Live Pro. So there are certain configurations to do if you want to switch between one RGB camera to another. So in this demonstration, we are going to use ROS Kinetic with ASUS Live Pro camera. But if you use different ROS versions, you might want to check what is the default RGB camera that is supported by the driver, or how to change it to the camera that you have in hand. And after starting the driver, we need to convert the depth image into a laser scanner. So when you start the driver, the RGB camera is going to publish several types of images: raw images, compressed images, and also depth images, which contains also the depth information coming from the laser scanner. But we don't have any topic that provides the scan information. For this, it is necessary to convert the depth camera into scan readings. And to do so, we will use the package called depth image to laser scan, and the node it's called depth image to laser scan as well. So I put everything into a launch file because we need to remap the image topic to the correct image that is called here /camera/depth/image raw. I'm going to explain this more in the demonstration. So for this reason, I have defined a launch file, and a launch file is nothing but a file that is able to start one node or multiple nodes, and also to define the names of the topics and also provide the values of the parameters. So here we're going just to start one node, and then we are going to change the definition of the topic name from image into camera/depth/image raw, because this is the name of the depth image that we are going to use in order to convert the depth image into a laser scan values. And finally, we will open RVs and test with ROS topic echo, and also we will visualize the ranges collected by scan using RVs. So let's see how things work in practice. So the first thing that we need to do is to connect the RGB camera into our system. You have to connect it through the USB port. And if you work in a virtual machine like I'm doing, you will be prompted whether you want to connect the RGB camera to Mac or to Linux. So in our case, we will connect it to Linux because we're going to use ROS installed on Ubuntu in order to start the drivers of the camera and also collect all the information about it. So we click here on Connect to Linux. And in order to make sure that it is connected, we can go here to the connection settings. So I'm using Fusion. So, and here you go to USB and Bluetooth, and you make sure that ASUS PrimeSense device is connected to your virtual machine, to your Ubuntu operating system. So everything now is in place. And as we will be using OpenNI, so we need to make sure that it is installed. First of all, we do sudo apt-get update to make sure that our system is up to date. Okay, and then we will try to install OpenNI2 if it is not installed. So we use sudo apt-get install ROS. I'm using Kinetic version, and then OpenNI2. So we can install everything here. Will be upgraded, and then I'm ready to connect. Okay, so the first command that we need to do is actually to start the launch file, OpenNI2 launch, and then OpenNI2.launch. If you want to make sure that our camera is correctly started, we can use ROS topic list, and you can see here these are the list of all topics published by the camera now. So we have depth images. So this is what we'll be interested to. We're going to use one of these topics. We have also infrared images. We have also RGB images and so on. We can view one of these topics. For example, I can use these topics and open it with image view. I can use ROS-run image view, and then image equal, and then the topic name. And now you can see, okay, this is the camera, this is my mobile phone. Okay, it's working pretty much fine. I will put a bottle here. Okay, so you can see bottle of water just in front. That's great. Of course, we can also observe the depth image. So instead of RGB, I will use depth. So I'm going basically to use one of the topics here on the top, which is this one, camera depth image row. So let's use depth. And you can see here, this is the depth image. This is the room using a depth image. So you can see it's a grayscale color, and the darker it is, the closer is the object, and the brighter it is, the farther is the object. Basically, we're going to use this information in order to convert this depth image into a list of ranges. And for this, we need to convert it into a scan topic. So basically, the scan topic is the common name for the information coming from a laser range finder. And as you can see now, in the list of topics, I don't have any scan topic at all. Why? Because this driver doesn't actually generate any scan topics. In ROS, there is a particular package and particular node that converts a depth image into a scan topic. Okay, so we can use ROS run depth image to laser scan, depth image to laser scan. I can start this one, and now I'm going to make ROS topic list again, and you can find the scan topic again. Okay? But the problem here, if I make ROS topic echo slash scan, okay, nothing will happen. This is because I didn't specify the name of the image to the node depth image to laser scan. So since I didn't specify what is the name of the depth image, it was not able to make any conversion. So in order to specify the name of the depth image, I'm going to make image equal, and then I will specify the topic name. And of course, the topic name here is the depth image. Okay, so now if I do ROS topic echo slash scan again, okay, and now I'm getting values. So this is the array of ranges. Okay, so you can see this is the array of ranges that we are getting, and we have array of intensities as I have explained before. This is the information about the angle max, angle mean, angle increment, time increment, scan time, and all the different things. Now we are getting them. Okay, so you can see it is working. So that's why we need to convert the depth image into scan using the package and the node name depth image to laser scan. So this node is going to make the conversion. We need to specify what is the depth image, and then it's going to produce for us a scan topic, as you can see in ROS topic list. Okay, there is another way that we can do it using a launch file instead of every time writing the name of the image. So I can go here to ROS Essentials. In Perception, I have a launch file that I have created. For the launch file, it specifies the nodes that we would like to start. Okay, it's an XML file that specifies one or multiple nodes that we want to run at the same time in the launch file. So here the node name is depth image to laser scan. This is the name of the node that we want to create. This is the name of the package, and this is the name of the node. So this is the name of the node that we want to assign whenever you execute the node. And this is the actual name of the node, okay? And here we make the conversion or the assignment of the depth image into the topic image. Okay, so like we did here, this assignment image equal the camera depth image row, so we can use it inside the launch file using the tag remap. Remap, it means changing the name of the topic image into this one, so it's going to convert this topic into a scan topic. As such, now we can start the depth image to laser scan node by launching the launch file, okay, and how we can do it, we can use ROS launch. And now the file is actually in ROS Essential CPP. As you have already observed, it is in ROS Essential CPP, SRC topic 3, and the launch folder. So I put here the launch file, and then I can actually call this launch file. It contains all the information. Okay, depth image to laser dot launch is going to do the whole work. So it's going to start the node depth to laser scan, and it's going also to remap the image name. So let's do ROS topic list again, ROS topic list again, and then we can also make ROS topic echo slash scan. and you can see now the scan is working. So these are the list of ranges now that you collect. Of course, you can observe that some ranges are not defined, maybe error in the reading or problem in defining the value, either from the software side or from the hardware side. Anyway, later on, we will see how to process this information using ROS, okay? So we can, for example, calculate the maximum value, the minimum value. In the next video, I'm going to explain more the details about the angle mean, the angle max, and the different metrics. So you can see these values, they are expressed in radian, and we are going to verify that these values actually corresponds to minus 30 degrees and 30 degrees, because we know that the field of view is equal to 60 degrees. So I'm going to talk about more details in the next video. But now I would like to give you another means on how to visualize this information. It's actually very difficult to read this numerical information like this, so I want a visualization tool. And in ROS, there is a very nice and interesting tool that is called RViz. RViz, it means ROS visualization. And this tool allows to visualize different topics, and among them, the laser scan. So we can run RViz. So first of all, you have to make sure that RViz is installed. So in principle, it comes installed with the ROS installation. So you don't need to install it manually. And then what we can do, we can make ROS run RViz RV. Okay, and it's a graphical interface. For the moment, we don't see anything, because as you can see here, we have only some global options. We didn't specify any laser scanner topic, so we can add it using the add button here. But first of all, we need to fix the correct frame, and I'm going to talk about frames in the next chapter when I'm going to talk about transformations, because transformations are very, very, very important. But for the moment, don't worry if you don't know what are the transformations and what does it mean, these different frames. We're going to explain this. So now, when we start the driver of OpenNI2 that connects to the RGB camera, it's going to create some frames. And these frames are the reference frames of the camera. So there is a frame attached to the RGB cameras or to the depth camera. I'm going to use just camera link here, okay? So I'm going to select this one. So the error has gone. And now I'm ready actually to add a new topic. And of course, since I'm interested to laser rangefinder, so I'm going to select laser scan topic. And I can open the properties here, and they have the topic name. So the topic name, I can select scan. And you will see now, okay, so I have, this is the information because now I am in the room. So this is part of the room, and this is the corner of the room. So you can see the laser scanner, and now it is pointing to the cabinet and also part of the wall, as you can see. So it makes the corner, and I'm going now to put something in its front. Okay, so I'm going to put a button here, and you can see the button now is reflected in RViz. Okay, so if I remove the button, okay, so you can see that we have the corner of the two walls together. Let me put the button again. Okay, and you can see now the button is in the front of the laser scanner. So, and this is reflected in the RViz interface. Of course, we can play with the intensity of the visualization here. So let me put this to 0.1. Maybe it's too much. So I can put 0.5 or 4. Okay. Now, I remove that again. And the laser scanner provides us all the obstacles that comes in its front. And also, we are able to visualize the different obstacles. Okay, so now I have visualized the location of the RGB camera. Okay. This is a fixed frame, so I can put the camera link. Okay, and this is the position of the camera. And this is the obstacles in front of the camera. So in this video, I have presented how to access the Asus Live Pro RGB camera and how to start its drivers. Also, I have presented how to convert a depth image into a laser scanner topic, and how to visualize everything using RVs. In the next video, I'm going to discuss in more details the different parameters of the laser scan and also how to create a ROS node that subscribes to the laser scan topic and process. Bismillahirrahmanirrahim. Wassalatu wassalamu ala nabiyyina Muhammad wa ala alihi wa sahbihi ajma'in. Hello guys, and welcome back to a new tutorial on laser rangefinders with ROS. In this video, I'm going to demonstrate how to connect a Hokuyu URG04LX laser rangefinder with ROS Kinetic. And this particular laser is very popular and is used in many robotic platforms. As already explained in the introductory lecture, this laser sensor has a sensing range of around 4 meters and a field of view of 240 degrees with an approximate cost of $1,000. There are a number of steps that we need to follow in order to connect Hokuyu URG sensor and make it up and running with ROS. So first of all, we need to make sure that the URG node package is downloaded into our system, and then we have to run it using the command rosrun URG node. So this is a generic node that can be used in order to access and connect to many Hokuyu sensors, including the Hokuyu URG04LX that we are dealing with in this video. By running this node, all the information coming from the laser rangefinder will be published into a topic called scan. And the scan topic, as already mentioned several times, this is the common name of the topic for laser scanners data and information. So unlike the case of the RGDB camera, we don't have here a depth image that we need to convert to a scan topic, but we will have direct access to the scan topic as soon as we execute the node URG node, which is going to start the drivers of the laser scanner. However, there is one thing that we need to define, which is very important, and that is the transformation between the map frame and the laser frame. Of course, we will have a complete chapter on TF transformation in ROS, so don't worry about that if you don't understand what are transformations and what is TF. But to explain this in a very simple way, we're going just to tell ROS what is the location of this sensor into the environment. Okay, so since we don't have any specific location, we're going to say that this sensor is located at point 0, 0, 0 coordinate in X, Y, and Z coordinates, okay? And the orientation will be 0. So to do that, we are going to use the package TF and the node that is called static transform publisher, which is going to create a transformation between the map frame and the laser frame. As already mentioned, it is just specifying the position of the laser in the world, and you are going to say that this position is going to be zeros for X, Y, Z coordinates, and also 0 for the orientation for the angle. As already mentioned, we are going to talk about this into more details. For now, it doesn't matter if we put any kind of number here, because our objective is to visualize the sensor data and not to localize objects with respect to the world. So this is basically the simplest explanation. So just assume that we can define the position of the laser with respect to the world as being at the location 0, 0, 0, and at the orientation 0. That's all. And then after starting the static transform and the URG node, we are going to visualize the information of the scan topic, both using ROS topic echo and also using RVs, which is the ROS visualization. So let's see how it works in practice. Now we are ready to start working with the Hokuyu sensor. The first thing we need to do is to connect the sensor to the USB port. And then, as you can see, we need to choose connect to Linux, since we are going to work on the Linux environment. And now we are ready to start the driver. The sensor now is powered on. Of course, in order to run the driver, we need first to start ROS core, because we will use rosrun. So first of all, we need to start the ROS master node, and then we need to make sure that URG node is already installed. So what we can do sudo apt get install ROS Kinetic URG node. Put the password. So it's already installed on my computer. If it is not installed on yours, so you have to install it first. And then you are ready to start the driver. Rosrun URG node. Okay, now it is connected to the serial device and it starts streaming the data. So let me first close the connection. And before connecting, let's make ROS topic list. So as you can see, we don't have any scan topic for the moment. And now I'm going to start again the URG node. Now it is connected again. So I can use now ROS topic list. And as you can see now, we have the scan topic, okay? And different other topics, but we are now interested to the scan topics that contains all the information. As usual, what we can do, we can use ROS topic echo / scan. And here we are getting the array of ranges, okay? So this is the array of ranges. You can observe that it is much longer than the ASUS Live Pro RGB camera. So don't forget that here we have a field of view of 270 degrees, whereas with ASUS Live Pro we have a field of view of only 60 degrees. And basically this is now the minimum angle and the maximum angle in radian. If we convert this one into degrees, so we will find around -135. We can use a calculator just to check. Okay, so we have 2.3561 divided by 314 multiplied by 180. So it's around, yes, 135. So it's between 135 and -135. So the field of view here is actually 270. So now we are able to get all the information using ROS topic echo. Like we did in the previous video with the RGB camera, now we would like to visualize the laser scan. And for this we are going to use ROS run RVs again. And remember that RVs is the ROS visualization tool. As usual here, initially we don't have any scan topic because it's not in our list. So we can add it from here and we use laser scan. Then we can select the topic here, scan. But as you can see, we are still unable to see anything here. Because we have a warning, it says that there is no TF data. There is no transformation data. Now here we have a fixed frame map. Map is not defined, and there is no frame associated with the laser rangefinder, the Hokuyo laser rangefinder. So the difference is that when we started OpenNI 2, it already started with assigning frames to the camera. That's why we were able actually to visualize the laser scanner. But here with the Hokuyo sensor using this driver, URG node, it doesn't actually start any frame. It doesn't tell about what is the position of the sensor in the world. For this reason, we need to define this manually. How can we do that? So look now, there is an error. I'm going now to use transformation. As already explained in the introduction, we will use a static transform publisher between the frame map that represents the world, the environment, and the laser frame that represents the location of the laser. So as already explained, we're going just to use any arbitrary position. In this case, it's going to be 0 for the XYZ coordinates and also 0 for the orientation. Of course, I remember that we will talk about this static transform publisher with more details when we talk about transformations, because this topic is very important. But for now, as already explained, it's just a matter of defining a certain location for the laser scanner in the world. And this location will be just the center. Look now, when I start the TF transformation, okay, I no longer have any problem here. So you can see now the map frame is defined and I have also the laser frame. Both of them were defined. So first of all, we can improve the visualization here by just putting the size equal to 0.5, and we can have some observations. So the first observation that we can do now is that the field of view of the URG laser scanner is much larger than the ASUS Live Pro camera that we described in the previous video. So you can see now we have a complete coverage of almost the room and with an angle around 270 degrees. You remember for the ASUS Live Pro camera, we only had this portion that was covered, which represents almost 1/4 or 1/5 of this total coverage by the URG laser scanner. We can also show the position of the laser scanner by adding here the axis, so it's here in the middle. So it can observe, this is 180 degrees in the left and the right side, and also it can go even backward. Okay, so as you can see, I am sitting here now. I am moving, and you can see now the laser is actually detecting my motion as well because it's looking even behind. Let me put an obstacle in front of the laser scanner, and as you can see now, okay, so I'm putting this keyboard, and you can see now this is the location of the keyboard in front of the laser scanner. So this shows actually great capabilities for URG laser scanner to detect obstacles at a wider field of view, and this is a major advantage as compared with the ASUS Light Pro RGB camera. So this matters a lot, especially if we use the laser scanner to build maps using SLAM algorithms. Building maps using SLAM with larger field of view will result in a better accuracy of the maps. And this is why the cost of the laser scanner depends actually on the effective field of view. Now we were able to visualize the laser scanner in RVs and also using Rostopic list. The next step is to use the information coming from the laser scanner, process it, and use it to develop some application logic for the robot. So in the next video, I'm going to show you how to create a ROS node and how to subscribe to the laser scanner topic and calculate different statistics. For example, if you want to calculate the maximum distance or the maximum range, the angle of the maximum range, what is the minimum distance, what is the distance at a certain angle. So all of these parameters can be calculated using ROS. First of all, we need to create a node, and then we create a subscriber with the topic scan, and then in the callback function, we can process all the information coming from the scan topic. So let's see how it works. In this video, I'm going to show how to save the laser scan information into a ROSBAG file and how to play it again. Of course, this operation is useful because not everybody has a laser scanner, and later on there will be some assignment and exercises to do, and probably not all of you would have a laser scanner to get the messages from a real device. So I'm going now to record all the messages coming from the scan topic, and later on we can play them again so that the scan messages will be coming as they are really coming from the real device. Let's see how can we do that. First of all, I need to start ROSCore, and then we need to start the driver of the laser scanner. In this case, I'm going to use Hokuyo Laser Rangefinder. Okay, and then I will create a static transform publisher, as you already know. So in order to define the location of the laser with respect to the word frame, as I already explained before. And then we need to create a new folder where to put the log information. I'm going to call this one bag files, okay? And then we go to the bag files. Of course, initially it is empty. Before starting the logging of the messages, let me run RVs first. Run RVs. And as usual, we need to add the information about the laser scanner. So here we need to select scan topic, the laser scan visualization. We can increase the font so it is more visible, and I can also show the frame of the laser itself, which is this one. Okay, now I'm ready to start recording. So what I can do in order to record, we use ROSBAG record -A. So -A is going to record everything. I can specify whether I want to record one topic or two topics, but I'm going to record everything. And now, as you can see, it starts to put into a log file all the messages coming from these different topics. So in the meanwhile, you can see now, this is the laser scanner. Everything is being recorded. I'm going now to move in front of the laser, and you will see me moving right now in front of the laser. So later on, when we are going to play back again, you will see that the same motion is going to be replayed in the same way. So I'm going to start moving now, and you will observe this. Okay, so you can observe there is a series of points that is now moving. Okay, so this will be moving around in front of the laser, which is capturing this. So everything is being recorded while I'm moving. And then later on, I'm going to show you when I replay this, it's going to replay exactly the same motion. Now I'm coming too close, going backward. Okay, so now we have saved everything. I'm going to close everything now. We close RVs, so we can stop recording. I will stop everything now, even the driver and the ROS score node. Okay, so let me run ROS score again. And now I'm going to run RVs. I will add the laser scanner. I will add also the axis. Of course, there is nothing to show now because nothing is playing. There is not even a topic here. And now the idea is actually to play again. So looking at the folder of the back files, you can find now a new log file that is called, this is the date of today, .back. So we can play this file again. We can look at the information about the back file using ROSBAck info. So these are all the information. This is the path. This is the version, the duration, the start date, the end date, the size in megabyte, the number of messages stored, and the different topics that were monitored and recorded. So now if we want to play the back file, we can use ROSBAck play and then the back file. So now it is playing. Now I can play the scan message. And you will observe now that the same operation that was done with the real sensor are going to be replayed and repeated. So we wait a little bit and we will see now the object moving around. Okay, so the motion has started now. You can see here, this is the place where I was moving. So it's going to continue moving in the same way that it was recorded. Okay, now the object is moving. So we can actually use the same back file in order to work with the scan topic, process the information coming, and develop algorithms. So this is a useful method if you want to store particular events into a back file, and then you can play them and develop your algorithm and test your algorithms with respect to the event that are stored in the log file. So this is when I come close to the sensor, then going backward, then we will stop the recording. Okay. Okay, so the back file is going to continue to play until the end. Now it stops automatically. And you can see everything was stopped. Okay. And this is the way how we can actually store the information about not only the scan topic, but any kind of topic. It can be recorded using ROSBAck and then replayed again. In the next video, I'm going to show how to write a ROS node that subscribes to the scan topic, whatever it comes from a back file or it comes from a real laser. And then I will show you how to process this information both in Python and C++. بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Welcome back to a new tutorial on robot operating system, and now it is time to write ROS node as a subscriber to the laser scanner. In the previous videos, I have presented laser scanners using RGB camera and laser range finders, and I have also presented how to connect them, how to visualize them using RVs, how to store them using ROSBAck, and how to replay them from a ROSBAck file. In this video, we are going to write our first ROS node to subscribe to a laser scanner topic and to process it. Let me first clarify the process. First of all, we need to start the drivers of the laser scanner, whatever it is, URG or the ASUS Live Pro camera or any other device if you have. Another alternative, if you don't have a device, you can also start a ROSBAck file, which you can find on the GIT Hub repository of the course. And then you have to make sure that the scan topic is available so that when you subscribe to it, you are sure that you will receive messages in the callback function. Then you will write a ROS node that will subscribe to the scan topic, and then in the callback function, it will receive the scan messages and process them, for example, to calculate the mean range, the maximum range, the average range, and the different other statistics. So let's see how it works in practice. Let's get started with the Python code of the ROS node subscriber to the laser scanner. So here in topic 4, perception 2, laser, we can click on scan subscriber.py. So basically this file, in the main function, it initializes a node that is called the scan node, and here it will just start a new subscriber using rospy.subscriber, and here it will subscribe to the topic scan. This is the type of the messages, laser scan, and this is the name of the callback function, scan callback, okay? So we need to import the laser scan message from sensor msgs.msg, and also we define the scan callback, and data here will represent the scan data that will be received from the sensor. Let me connect now the URG laser scanner just to make a refresher. I will start ROS core, and then I will start the URG node, and now I'm going to make ROS topic list. So this is the scan topic that we are going to subscribe to it. And then what data we are going to collect is the data that we get inside the topic. So we can make cross topic echo scan. Okay, and this is the data that we will collect. So basically we have angle mean, angle max, angle increment, time increment, scan time, maximum range, minimum range, and then we have an array that contains the list of ranges from the minimum angle to the maximum angle. Okay, so remember that these angles are expressed in radian. So basically this is the structure of the scan message that we are going to receive, and we can extract this information here in Python. Okay, so in the scan callback method, we have the received message data, so let me call it scan data. And basically in the scan callback, we're going to print some statistics. For example, we will print the minimum range value, the maximum range value, the average range value, and also the average between two indices. So here I have defined a couple of math functions I'm going to describe below. For example, this function is going to return the minimum range and the index of the minimum range, okay? And this function is going to return the maximum range and the index of the maximum range. Of course, it takes as input the array of ranges. So here we have an array that is called ranges. Inside the callback function, we have the object scan data, and inside scan data, we have the array ranges. So this array will be the input to a method that I have created below. I'm going to explain. And then we're going to extract the value, the maximum range, so the maximum value in ranges, and also the index that corresponds to the maximum range. We will do the same for calculating the average value, okay? And we put the array as input here, and also the average between two indices. So this is the average value among all the values in the ranges, and this is the average value, for example, between index 2 and index 7. So we can use any kind of index here, whatever you want, the left side, the right side, or in the middle. Okay, let me correct the spelling error for these two methods. So Python is actually a very powerful language, and it has a lot of tools and libraries that make it easy actually to extract the maximum values from an array. For example, here the method mean range index that we are going to call above here, we're going to apply the function mean that is already defined in Python, which takes an array as argument, and mean ranges is going just to return the minimum value. Okay, so the minimum range is going to be returned by the method mean ranges. And then we can use ranges.index, and then we will provide the minimum range here. It's going to return its index. That's why this mean range index is going to return both the range and also the index. And this is the output of the method here. It's going to be two values, the minimum range and the index of the minimum range. Same thing will be for the maximum range index. Okay, we're going to return the maximum range and the index of the maximum range using the same thing. Instead of using the method mean, we're going to use the method max, which is already defined in Python, okay, and can be applied on ranges. Okay, something very important here. So you have observed that some of the values can actually be equal to none. So let me check here. Yes, you can see. So we have to deal with them. We need to find the maximum value such that it is different from none. Okay, whatever it is, the maximum or the minimum value. Usually for the minimum value, we don't have any problem. But for maximum value or calculating the average, if you don't discard the none values, okay, at the end the result will be also equal to none because it is not defined. So what we can do here, we can filter out the none values. So ranges is equal every x inside ranges if x is not none. So we use here the function is none that is defined in the module math. Okay, so if it is not none, in this case ranges, okay, will contain the x value. Otherwise the x value will be discarded. So here we're going to discard all the none values so that when we apply the mean on ranges and the max on ranges, we are sure that we are going to apply them on the double values and not undefined values. So same thing for ranges. First of all, we filter the ranges from the none values or undefined values, and then we're going to use sum ranges is going to return the sum, and then we will divide the sum by the length of ranges. So here we need to do a small casting on float such that here we return a float value for the average range. So the average range is the sum of all ranges divided by the total number of ranges. And the same thing is for the average between two indices. So here, instead of specifying only the range, we specify the range and also the first index and the last index. We filter out the undefined values, and then we slice the array. So in Python, we can use a slicing. So we're going to select all the values in ranges from index I to the index G plus 1, okay, because this index will be excluded. So if we want between I and G, we need to make it between I and G plus 1. And finally, we're going to make the average on this sliced array, okay, the sum of the sliced array divided by the length of the sliced array is going to return the average distance between these two indices. Okay, and that's pretty much it now. In the callback function, we're going just to call the different methods that we have defined below, and then we can now run our program and check how it works. Okay, so now we have already the driver running, and now I can run ROS essential CPP, and then we have scan subscriber.py. Okay, so you can see now it is actually calculating. Let me stop it. Okay, so the minimum range value is 0.07, the index is 44. Okay, the maximum range is 5.19, so you can see it can look up to 5 meters, and the index is 59. The average range is 1.76, and the average between the indices 2 and 7 is 0.018. Of course, these values can change from one scan to another, so you can see that we have the callback function is going to be called 10 times a second because it operates on 10 hertz. Okay, so if we make ROS topic echo, okay, this is the scan time. It's 0.1. It means every second there are 10 scan values. Okay, so this Python code is actually able to find the maximum value, the average value. And of course, here we just display the information. But now, for example, if we have the laser on a robot, we can use this information in order to avoid obstacles. For example, we can try to find out what is the minimum range to the robot, and then if it is in the left side, we try to move toward the right side, and if the obstacle, the closest obstacle is the right side, we try to move to the left side, and so on. So we can develop application logic. For example, we can also make an alarm system, okay? If we have an object that comes very close to the laser, in this case, for example, you can make an alarm, or if the robot is moving, we can force the robot to stop, so that it doesn't crash to the obstacle. We can implement application logic by processing the information coming from the laser scanner. For the moment, as I already mentioned, we are just displaying the values, but now you have all the tools in order to implement the application logic. So we're going to have an assignment where you are going to practice on processing the laser scanner information in the callback function. In the next video, I'm going to show how we can write a subscriber in C++. In this video, I'm going to present how to write a ROS node in C++ as a subscriber to a laser scanner. In the previous video, we have written a node using Python, and in this video, we're going to write it in C++. You will see in C++ things are a little bit more complicated because we don't have the utilities that Python provides to easily calculate the statistics from an array like the minimum value, the maximum value, and the average value. So let's see how it works. Remember, in the Python program, we have already predefined functions that allows to calculate the minimum value inside an array, the maximum value, also the sum of all the values in an array. However, in C++, we don't have these utilities. For that reason, I have created some files. So the first file is called utility-lib. It's just a library that I have created, which performs a few computations. Like, for example, it converts radian to degree, degree to radian, and get the Euclidean distance between two different poses. So these are some functionalities that we may need or we may want to use whenever we work with laser scanner. And also, most importantly, this is another library where I have created a class that is called laser scanner, and it contains static methods. For example, there is a static method that allows to find the average range in a laser scanner between two indices, start index and end index. Some method that allows to find the maximum range, the minimum range, also the front range. The front range, it's in the middle of the field of view, usually at the angle 0 in the middle. So these are different functions that I have created and I have implemented in order to calculate some statistics for the scan messages that we will receive. Another function is called also is obstacle to close, that it takes a laser scanner message and start index and index to specify an interval of values and also a distance threshold. So it's going to return true if the maximum distance inside this interval is smaller than a distance threshold. The file laserscanner.cpp contains the implementations of these different methods. For example, to calculate the average range, we go from the start index until the end index, and we calculate the sum of all the values, and finally we divide by the total number of values. Of course, here we have to exclude all the values that are none. So we use std is none. If it is not none, we're going to calculate the average for the value. Some other functions also allows you to give you the index, convert an index to angle. So if you give an index inside this array, it's going to give you what is the relative angle. Okay, don't forget that we have the angles in the field of view between angle mean and angle max, and every measurement corresponds to an angle and also corresponds to an index inside the array. So if I know the index, I can determine what is the angle, and if I have the angle, I can also determine what is the index. So these are just some computations that we do in order to find the index from the angle and the angle from the index. And all the other utilities, for example, to calculate the average range in the right side or in the left side or in the straight direction, getting the minimum range. So we're going to have initialize a mean index, and every time we find a minimum value, we're going to update the mean index, and finally we will return the minimum value with the mean index. So you can look at the implementation of laserscanner.cpp, and don't forget that all the methods here are static, so we don't need to create an object. We can just call all of them by the name of the class. These two libraries are located in the LaserScan folder inside topic perception02 laser folder. And now let's look at scanSubscriber.cpp, which has the same structure of the Python code. So we have the main function, we initialize the node, we give it a name, so the name node will be scanSubscriber.cpp, and here we create a node handle, and then we will create a subscriber to the topic scan. And then we define the callback function that is called scan callback. So scan callback is going to take laser scanner message, okay, and then this is the header definition of the scan callback function, and this is its implementation. It is similar to scan subscribe, where we print the minimum value, the maximum value, the average value. This is the Python version, and even in C++ version we print the minimum value. So how to print the minimum range? We use the static method laser scanner get minimum range, and we put here the scan message received. Same thing to get the maximum range, same thing to get the average range. So the average range is going to be computed between the start index 0 and 600. And also here, this is a testing of the method is obstacle to close, which takes a scan message, start index, and the distance threshold. So here, every distance that is smaller than 0.69 is going to write the obstacle is too close. Of course, you can change the value of the threshold depending on the requirement of your application. Something very important to note here, in order to use the laser scanner, get minimum range, and the different methods that were defined in this file, so it is important to import the laser scanner.h header file, okay, which is located in the laser scanner folder. So we have to include the library, and also this library, it includes the utility lib library that I have presented first, that contains a few methods like converting radian to degrees, degree to radian, and so on. So you can see here that laser scanner includes utility lib, and scan subscriber.cpp, it includes laserscan/laserscanner.h. Of course, in C++ is not like in Python. These inclusions have to be reflected in the CMake list. So what we should do before being able to compile, we need to add these libraries into the CMake list. So first of all, we need to use add library instruction. Okay, so we specify the library name that we want to produce. I'm going just to call it utility library, and then we provide the source file of the utility library that we want to add to the CMake list, to the build system. Okay, it is located in src topic file perception2 laser/laserscan folder. Okay, this is where I have put the library, and then utility lib.cpp. We do the same thing for the laser scanner. So I'm going to create a library called laserscanner lib, and then I have to specify what is the source file for this library. And since laserscanner lib includes utility lib, in this case we have to add an instruction target link libraries, laser scanner lib, utility lib. So this means that utility lib is included in the laser scanner lib. This will tell the build system that the laser scanner lib is using the library utility lib. And here these are two instructions that we have to do to add laser scanner lib into the Catkin libraries and also add it as a dependency to Catkin exported targets. So these are the two libraries that we need to add in our build system. And of course, we need to add an executable for the scan subscriber as we did for other nodes. So we need to add executable like we did for the other nodes and services. I'm going to call it scan subscriber CPP. And this is the source file of the scan subscriber.cpp, okay, which is going to be used to create the executable. And then we need to add all Catkin libraries to scan subscriber CPP. And also, since scan subscriber includes laser scanner, so we need also to add target link libraries, scan subscriber CPP, laser scanner, okay? This is because of the include statement that we have in scan subscriber or the laser scanner.h. These are the changes that we have to do in the CMake list whenever you include your custom libraries into your ROS nodes. So to summarize, first of all, we needed to add the library utility lib, which contains some basic functionalities to convert from radian to degree to radians. And then we need also to add the laser scanner lib and also to link between laser scanner lib and utility lib because laser scanner includes utility. And finally, when we create the executable, we need also to add target link libraries between scan subscriber and also laser scanner lib. So now we can try to run this code. First of all, I'm going to run roscore, and then I will go to the back file that we have created last time, and I'm going just to play it so that we have some scan topics. And this is the benefit of having back files, so I don't need every time to connect again to the laser scanner and start the port and so on. So just for testing and debugging, I can use the back file and replay it again. So I'm going to use back play. Now it is playing. Of course, I'm going to go to Catkin and compile again. After making all the changes, we need to compile everything again. Okay, so I have already compiled that. And then making ROS run, ROS essential CPP, and then scan subscriber underscore CPP. This is the new node that we have created. And you can see now, we are getting the minimum range. This is the maximum range. Okay, let me change it. It will be maximum range. So after doing that, I need to compile again. Okay, so it has created again the same node. I'm going to replay again the back file, and then we can run our program again. So you can see now it's giving the minimum range, the maximum range, the average range, and also when it is slower than 0.69, like in this case, we just return obstacle is too close. This is the condition that we have set in our program to detect whether an obstacle is too close or not. Okay, so to summarize, in this lecture I have presented how to process scan images in C++ using a ROS node in C++, and for this I had to create a new library that is called laser scanner that contains different methods that allow to process the laser scanner message, because in C++ there is no ready-to-use methods that allows to process arrays easily like it is in Python. Now we have everything in hand in order to use the laser scanner to develop a robotic application that allows to control the motion of the robot using the information coming from the laser scanner. For example, a very simple project will be to make a robot move until the minimum distance to an obstacle is lower than a certain threshold. In this case, we stop the robot for safety purposes. This is one of the many applications where we can use laser scanner in order to control the motion of the robot.